Homework last night was page 664, diverging and converging mirrors, curved mirrors, the mathematics of it. Any issues with those 3 questions on page 664? Sorry, those 5 questions on page 664. Number 5? Oh, you know what? I remember what that question was. Yeah. Not a surprise there that we need that one. Yeah. Number 4. Okay. Let's take a look at 4 and 5 here. 4 says a 4 centimeter high object is placed 15 centimeters from a concave mirror. Concave mirror. Usually we see the terms converging and diverging. This one is concave versus convex. Is a concave mirror converging or is it diverging? Alex, is a concave mirror converging or diverging? Concave lens would be diverging. Concave mirror would be converging. So that's a positive focal length. Okay, we have an object height here of 4 centimeters. We have an object distance here of 15 centimeters. We have a focal length here of 5 centimeters. And we're going to leave it as positive because it's a converging mirror. We want to determine the image characteristics. We won't bother using a ray diagram because we've already drawn all the ray diagrams. We'll do the math here. So if we want to find the image characteristics, basically, we got to start solving for things. Okay, start solving for things. Let's try this equation and see what we can solve for here. The focal length is 5, DO is 15, and DI is what we're looking for there. Let's plug some numbers in there. 5, 1 over 5, subtract 1 over 15. Then 1 over that gives me 7.5. DI is 7.5 centimeters. Even though we're not asked to find DI, we're going to use that to determine one of the image characteristics. Which one does this tell me now? Positive DI tells me that I have what? It's a real image, yes. Okay, let's say M is equal to negative DI over DO. Negative DI is negative 7.5 over DO, which was 15. That gives me negative 0.50. What does that tell us? A negative 0.5 tells me 2 things, actually. What's one of the things that it tells me? Ben, what's one thing that that negative 0.5 for magnification tells me? Yeah. What does it tell me, though? What does it tell me in terms of the characteristics? Cassie? It's smaller, right? If it's a number between 0 and 1, regardless of whether it's positive or negative, if it's a number between 0 and 1, the image is smaller than the object. If it's above 1, again, positive, negative, doesn't matter. If it's above 1, then it's bigger. So this is a smaller image. There's one more thing that it tells me, though. The negative tells me that, Tara, it's inverted. Now, technically, negative 0.5 could be an upright image if the object was upside down. Okay, but if we assume the object is right side up, and it doesn't say otherwise, so so we have to assume that the object is right side up, then the image in this case would be upside down. All right? Is that good? All right, question number 5. This is a bit of a harder question, or at least it seems like a harder question when we start off with this. Once we actually do it, it doesn't seem so bad. It says light from a distant planet is incident on a converging mirror. That means that F is positive. The image on the planet, the image of the planet, I should say, forms on a screen 45 centimeters from the vertex. That's going to be DI, and it forms on a screen, so that means it's a real image, therefore positive 45 centimeters. We want to find the focal length and the characteristics. So we have DI, and we want to find F. That doesn't seem like a lot. What do we know about the object, though? What do we know about this star or this planet that's out there? Yep. Okay, we know that it's really far away. And if it's really far away, if DO is really, really big, then 1 over DO will be really, really small, close to 0, right? James, answer this question for me. You get the easy one here. What's 1 over 1? Yes. I know sometimes when I ask you a question like that, you're like, is he trying to trick me? No, it's 1, you're right. Aaron, you're going to get a harder question. What's 1 over 2? Yes. Dustin, you're going to get the harder question still. What's 1 over 3? Yes. 0.33. Okay. Jace, what's 1 over 4? Okay, so as the denominator gets bigger, the number gets smaller, right? As the denominator gets really, really, really big, the number gets really, really, really small. So what we're going to say here, guys, is 1 over f is equal to 1 over do plus 1 over di. 1 over f is equal to 1 over, call it infinity if you want. Do is not really infinity because it's just a big number. But it's, okay, whether it's 10 to the 11 meters or whether it's infinity doesn't really matter because basically that number gives you a number that's pretty much equal to 0. Di is 45 centimeters. That's a small number, but it's not close to 0. So 1 over f becomes equal to 1 over 45. That means f is equal to 45 centimeters. So the focal length is 45 centimeters. Now what about the characteristics? What about the characteristics? Let's say m is equal to hi over ho equals negative di over do. We don't know anything about the object, the height here. So let's just say m is equal to negative di, 45, over big number. So what is this magnification? Well, it's a really, really small number, a negative of a really, really small number. I don't care what the number is, but it's small. Approaching 0, in fact. Some of you are probably thinking, well, wait a second, that doesn't make sense. You're using a telescope here. Doesn't it magnify it? Let's think about that. Okay, you're looking at an object that is a planet. You see the entire planet through your eyepiece. You're not making that planet bigger. The image is going to be smaller than the object. You don't have a magnification that is greater than 1. It's going to be smaller than 1. In fact, a lot smaller than 1. If you look at the entire Earth from the International Space Station, okay, through a telescope, or from far off in space, and you can see it through this tiny little 2-inch diameter lens, then clearly the image has got to be way smaller than the object. We will end up with a magnification that's really, really small, and it will be negative. Now, what does the negative tell me? We know that the image is smaller, right? That's the first characteristic. It's smaller because we got a really, really small magnification. What does the negative for the magnification tell me? The image is what? Jake, the image is inverted. Good. Now, really, when you're looking at a planet through a telescope, it doesn't really matter if you're looking at that planet right side up or upside down, right? Okay, if you really feel strongly about that, stand on your head and look through it, and then you'll see it right side up. Okay? It's not really a big deal. What else do we know about it, though? Smaller, inverted, and what? Yep. How do you know it's real? Because they tell me that it's projected onto a screen. I don't need the whole solid dotted lines thing. I don't need the whole positive DI. They tell me it's projected onto a screen. They basically tell me that it's a real image there. All right? How many people got that? Without just looking at the answer. Anybody do it differently? Get it, but doing it differently than I just did it? No? Okay. Yesterday, refresh your memory on the concept of diffraction. We talked about it a little bit in Physics 20. but yesterday we spent some more time on diffraction and then the process that kind of goes along with diffraction often, which is interference. Diffraction, as you know, is the spreading out of a wave around a barrier or through an opening. Okay, this is a photograph of diffraction taking place by water waves. Here's my waves. They go through the opening here in the barrier, and then they spread out like this. They're not bending. They're just spreading out. Now, this diffraction that's taking place down here, when it's water waves, I can see it pretty clearly. Right? I can see the diffraction taking place. The same thing will take place if we shone light through that opening. Get rid of the water. Shine a beam of light through that opening. The same thing takes place, but you're not going to see this diffraction taking place because the light's not reflecting off of anything. The only difference here between the water waves and the light waves, we can see the water waves, we can't see the light waves. Right? Make sense? Our next page shows us two openings where we have diffraction taking place right here. And then we have diffraction taking place from this one as well. These water waves will encounter each other and interfere with each other. So when we have two crests or two troughs that encounter each other, cross each other, then we get constructive interference, a big crest or a big trough. But if we have a crest meeting a trough, then we get destructive interference, canceling out. We end up with nothing. We end up with a flat area of no waves. You can see the pattern formed here as a result of that interference. You can see an area of constructive interference here and here and here and here. Big waves, big crests and big troughs. But you can also see these areas of destructive interference here and here and here, where we have canceling out of the waves. The crest meets the trough, no wave, just flat, calm water. Again, the same thing will happen with light, but we're not going to see it because the light's not reflecting off of anything. If we want to observe this with light, if we want to prove that this is actually happening with light, as opposed to just taking my word for it, then what you got to do is put a screen up here. Put a screen up here. When the areas of constructive interference, the big crests and the big troughs encounter or strike this screen over here, then you get a bright spot. Where the lines of destructive interference strike the screen, you get, I call it a dark spot, but really what it is the absence of light. It's not dark per se, it's just there's no red spot because the red light that's shining on it isn't reflecting off of it. So you get bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. Let's magnify it a little bit and focus just on that screen. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on both sides. We're going to call this our central maximum, our central bright spot, our central antinode. This would be our first order, our second order, our third order, or fourth order maximum bright spot antinode. 1, 2, 3, 4 on the other side as well. In between, we have our first order dark spot, which we're going to assign a number of 0.5 to. Second order dark spot, third order dark spot, fourth order dark spot, and so on the other side as well. If we were to, by the way, plot a graph of intensity versus position, then it would look something like this. You can see that the intensity is high when we have a bright spot, and then the intensity is low when we have a dark spot. High bright spot, low dark spot, and so on. Again, this would correspond to the central maximum, first order maximum, second order maximum, and so on. Now, let's take a look at the two equations that I showed you yesterday. And identify what each thing means. There's a picture of the two openings, the two slits, and the screen, and the pattern that's produced on that screen. My two equations look like this. Lambda is equal to d sine theta over n. We said that's valid all the time. Lambda is equal to xd over n times L. We said that's valid some of the time. When? Well, we didn't really tell you when it's not valid yet. We'll worry about that in a few minutes. D, this value d right here, lambda is the wavelength, right? That's easy enough. D stands for what? Where would we label D on this diagram here? Good. From one opening to another. The distance between the slits, the distance between the openings. What about L? L's the next easiest one. Brendan, you got this one? Okay, folks. Aiden, you got this one? What's L stand for? Yep. No, you're getting that mixed up with something else. I'll come back to you in a minute. Give me the same answer for the next question I ask you, okay? Because it's going to be the correct answer to your next question. Nick, what's L stand for? Right, this distance right here. Listen carefully. D will always be a small number. L might not be a big number, but it's going to be bigger than D. L is always going to be a number that's bigger than D. Okay, if you get these two mixed up, okay, in the end, the bigger number, assign it to L. The smaller number, assign it to D. Aiden, what's X stand for? Could you say it? Could you say it, please? Yeah, so not the difference, but the distance between one maximum or minimum and another maximum or minimum. So it could be this. It could be this. It could be this. Or it could be this. It can be anything we want as long as it represents a distance between a maximum or minimum and another maximum or minimum. The trick there is recognizing that n has to be consistent with that. The value of n, in this case, would be 2. It's the difference between the maximum or minimum number. 4 minus 2 is 2. For this one, it would be 3. 3 minus 0 is 3. What about for this one? What about for this one, Lucas? It goes to the in between 1 and 2 there. Good. So we're going from 1.5 to 4. 4 minus 1.5 is 2.5. And this last one, this is the toughest of the 4. Aisha, she says, why'd you have to pick me for the hardest one? But then she said, yeah, you know what? I know the answer to this. Aisha, what is this one? It's 2.5. Good. So we're going to say 1 minus negative 1.5, or you can say 1.5 minus negative 1. Either way, you get 2.5 there. It doesn't matter what you make x as long as n is consistent with x. Finally, theta. The only thing we haven't identified yet, theta. Theta is an angle measured from the central maximum to the second order minimum, to the fourth order maximum. It doesn't matter. Just like x doesn't matter, except you got to be consistent here. In this case, n would be 4. 4 minus 0 is 4. In this case, n would be 1.5. 1.5 minus 0 is 1.5. Jake, question? Yep. It should be xd over nl. Yeah. Let me just take a peek here, Jake, because I have the equation written down as I gave it to you. Yeah, XD over NL. Jake, if it was XL over NL, then it would be X over N, right? So I think, you just wrote it down wrong. It's on your data sheet, so don't panic about that, right? You can always check that data sheet, but you want to write it down the right way as well. Okay. We had, I believe it was 3 questions on this for homework. Those 3 questions were on page 689. We won't worry about the color in number 3. Okay, don't panic about that. Although it was violet and I was using a violet, did you notice that? Violet pen, violet color. What a coincidence. I should buy a lottery ticket tonight. Oops, already have. Any issues with 1 to 3 there? One and two? 1 and 2, really? You got 3? Okay, let's take a look at 3 then, because 3 is the harder one. So maybe let's take a look at 2 and 3. Okay. Number 2, blue light of wavelength. This is the wavelength, right? We don't like those units, so we're going to convert that. 2 slits that are this far apart. This is the distance between the slits, little d, but we don't like those units either. We want to find the angle of diffraction for the 3rd antinodal line. So here's my central 1, 2, 3. We want to find this angle right there. What's n going to be for that? Jake, what's n for that one? 3. So you got 2 equations. Since you're looking for the angle, you're probably going to use the one with the angle in it. Let's say lambda is equal to d sine theta over n. This is valid anytime, so you don't need to worry about having to decide whether you're allowed to use it or not. If you're dealing with diffraction interference, it's valid. You can use it. Okay, my suggestion for this one, since you're solving for theta, is probably plug your numbers in first and then rearrange it. Just simplifies it just a little bit here. Lambda is 460 times 10 to the minus 9 meters. D is 0.55 times 10 to the minus 3 meters. And n was 3. So let's pull out the calculator here again. 460 multiply that by 3 and divide it by 0.55. And now let's take the inverse sine of that. Make sure you're in degree mode. We're going to get a small angle here. We almost always get a really small angle here. Okay, I don't know what its value is, but typically it's an angle that's, probably less than 5 degrees, oftentimes less than 1 degree. What do I get here? 0.14? Oh, the answer's right there. 0.14 degrees. Okay, that fits with what we expected, right? We expected a small number. That's what we got. You good? Jake, is that okay? Okay. Number 3 is a little bit of a tougher question. I drew the little diagram here to determine what n was. Boy, number 3, it's really helpful to draw the diagram for number 3. This one says the second nodal line. A nodal line is a dark spot, a minimum. So let's draw this one out. Okay, central maximum, first order maximum, second order maximum. We're dealing with the second order minimum where n is 1.5. So we're going to say 1.5 minus 0 is 1.5. We're going to say the angle is, again, you can see it's a really small number here. D is 0.40 times 10 to the minus 3. We want to find out what lambda is. And n is 1.5. Do the math there. Should work out to be this, 4.4 times 10 to the minus 7. You shouldn't have to identify that that's violet light. You may have to identify that it's visible light. Okay, but in the end, you guys know how to do that, right? You can convert that to a frequency and then compare it against those 3 ranges that we memorized, what, about 2 days, I think, into this unit. Okay. Okay? I want to draw this out again. Bright spot, dark spot, bright spot, dark spot. That's my screen. Here's my openings. Okay, this is going to be our central maximum, 0, 1, 2, 3, 0, 1, 2, and so on. This is going to be represent L. And let's say I've got a value of X that's from the first order maximum to the third order maximum. Let's change that to 1, 2, 3. Doesn't really affect what we're doing here, but it was wrong, you're right. Let's say you've got a value of X. Let's say you've got a value of D. Let's say you've got a value of N, which would be, in this case, 2. And let's say you've got a value of L. The equation that seems to fit that is that second equation, lambda is equal to xd over n times L. But I've told you that it's not always valid. This is an approximation. It's not a perfect equation. It never is, no matter what. It's always an approximation. But for really small angles, it's a very, very good approximation, so that to the right number of significant figures, you'll get the exact correct answer to 2 or 3 or 4 digits, whatever you're supposed to round it to. Past that, it may not be exact, but we don't really care what it is past the right number of significant figures. For small angles, angles that are less than about 10 degrees, this is going to be just fine. Now, strict criteria for these questions using this equation is the angle smaller than 10 degrees? If it is, go ahead and use this equation. But I've developed a little rule of thumb so that if we're not given the angle, I mean, to me, if you're given the angle, if you have the angle and it tells you it's 7 degrees, or it's 12 degrees, or it's 6 degrees, or it's 38 degrees, then why wouldn't you use the equation that we know is always valid, d sine theta over n? I mean, it only makes sense to use this equation if you already have the angle. So if we have the angle and we use this equation, then how are we supposed to determine if we're ever going to use this equation? Well, here's the rule of thumb. If L is greater than 10 times x, that's not an exact science. That's an approximation as well. That's our rule of thumb. If you calculate the value, you take the value of x and multiply it by 10, and that number is greater than L, don't use that equation. If that number is smaller than L, then go ahead and use that equation. You will never go wrong by using that rule of thumb. There will be the odd time when that rule of thumb excludes you from using that equation when you really could have used it, but that's rare, and that's just one of those things that we're going to say, okay, I can live with that. Okay. In that case, I'll go back to using this equation. We'd have to find an angle, and I'll show you how to do that in a few minutes. A little bit more work, okay, but it's worth it in the long run. Every time you want to use this equation, I want you to go through this test. Is L greater than 10 times x? If it is, great, use the equation. If it isn't, well, you better get theta so that you can use this equation. How are we going to get theta? Well, if this is x, and this is, bad example here actually, has to be measured from the central here. If this is x, and this is L, then we could solve for theta using the tan function. Get a value for theta. Put it into this equation. Now, we can always do that if we're measuring from the central maximum. But if L is greater than 10 times x, why would we? Why would we go to the bother of solving for theta if we know that theta is under 10 degrees because L is greater than 10 times x? So do this test if it looks like you want to use this equation. And if you pass the test, then use that equation. If you fail the test, then calculate theta and go back to this equation that we did in our homework. All right? Let's take a look at an example problem and see what comes out of this one. It says a student measuring the wavelength of light emitted by krypton gas directs light onto two slits separated by 0.264 millimeters. We don't like this. We don't like this millimeters there. Okay, this is going to be D. This is going to be L. The distance between the second bright spot and the central. Okay, 0, 1, 2. Okay, n is going to be equal to 2 there. X is going to be equal to 0.0118 meters. Right, this is x. We don't like those units though. We want to know the wavelength. We want to know the wavelength there. It looks like this equation is the one we're going to use, xd over n times L. Looks like it. We got x, we got d, we got n, we got L. Perfect, right? Are we allowed to use it? What's the test? Is the angle smaller than 10 degrees? I don't know. I don't know what the angle is. What's the test? What's the rule of thumb test? Take x, times it by 10. Is that number greater than 3? Is 10 times x greater than L? Is it, Oliver? Is that number greater than 3? No. So we're allowed to use that, right? Tell you what, 9 times out of 10 you do that test, you're going to pass the test. 10x is going to be less than L, so that equation is going to be perfectly valid. 9 times out of 10, maybe even more than that. But you've got to do the test just to make sure. Okay, this equation is valid. X is 0.0118. D, 0.264 times 10 to the minus 3 meters. N was 2, and L is 3 meters. Right now, without knowing what the answer to this is, you should expect to get an exponent that's 10 to the minus 7, because that's visible light. Almost always going to be visible light. Five 5.2 times 10 to the minus 7 meters. Is that okay? Remember, if you see your givens and it looks like this equation is the one you're going to use, then do the test. Is L greater than 10 times x? If it is, go ahead and use it. If it isn't, then get theta from x and L and go from there. Okay? Going to give you a couple questions to work on here. I'm going to give you just a few minutes to work on because I want to give you one more example problem as well. So literally probably about 4 minutes. See if you can get the first one done just in case you have any trouble with it, okay? Then we'll move on with another example and leave these for homework here. Sarah? Yeah. Here's one more example for you. This one says a diffraction grating has 1,000 lines per centimeter. What does that mean? Well, it's kind of like having D. This is what we've been doing is called Young's double slit experiment. We have two slits, hence the term Young's double slit experiment. It was first performed by a guy named Thomas Young, 100-ish years ago, 100 and some odd years ago. When we talk about Young's double slit experiment, we have two slits or two openings. When we talk about a diffraction grating, we have hundreds or even thousands of openings. But here's the thing. When the light goes through two openings, we get this interference pattern produced. When the light goes through 6,000 openings, we get effectively the same interference pattern that's produced. So we're going to get the same thing produced here in this example as we have in the other problems that we've done yesterday and today. The difference is that this time we have this number we don't recognize. This number is 1 over d. When you have the number of lines per centimeter in a diffraction grating, Aiden, then it's not d, rather it's 1 over d. If you want to find d, Aiden, put it away, please. Okay, fair enough. Yeah, fair enough. Sorry. You want to find the value of d here? Let's flip it over. D would be 1 over 1,000, which would be 1.0 times 10 to the minus 3 centimeters. Now, we want that value in meters, so now we're going to convert it to meters. 1.0 times 10 to the minus 5 meters. Okay, that's d. If you're given a diffraction grating with lines per centimeter, then get d by flipping it over, by taking the inverse of it. 1 over 1,000. That gives you not lines per centimeter, but rather centimeters per line, which is the distance between two of those 1,000 openings. Okay, now we get the value of d. We get the value of L, it's 4 meters. The first order bright fringe, the central maximum, n is going to be equal to 1. X is going to be equal to 0.192 meters. We want to find lambda. I want to use this equation because we got all the variables that fits there. Now let's just do our little test. 10x equals 1.92 meters. Is L greater than 10x? Brendan, is L greater than 10x? Yes, it is. Are we allowed to use that equation? Yes. Okay, 9 times out of 10, you're going to pass that test. You just do it every time just in case. Okay, we have d now, right? We're given the value of 1 over d. We found a d from that. N is, what was the value of n? 1 times L, which was 4. So let's do the math on this one. 0.192 times 1 times 10 to the minus 5 divided by 4. Again, we get 10 to the minus 7, which we expect to get. It's almost always going to be 10 to the minus 7. Any different than the last question? Yeah, a little bit. We didn't have the value of d. We found it by flipping over the lines per centimeter. And then we did the same thing as we've done for the last couple of questions. Right? So the only difference, you got a diffraction grating, pay attention to that. If it's two slits, the Young's double slit experiment, then you got the value of d already. If you have a diffraction grating, then you've got the value of 1 over d, and you've got to take the inverse of it to get d. Then go at it like you have the rest of them. Hey, your homework for tonight. The questions that I assigned just a couple minutes ago that you were working on, page 691, in addition to these 3 questions on 693. That's it.